So now let's look at the Laplace transform of the complex exponential. So first of all, we'll compare it to the real exponential, which we did in the last video. So if we had the real exponential, it was e to the at. When we Laplace transformed it, we got 1 upon s minus a, where the real part of s was greater than 0. So that meant we had a pole whenever s minus a equals 0, or when s equals a. So it meant that we could position the pole along the sigma axis, depending on our choice of a, such that we have convergence on the right hand side of a. So now we're interested in the complex exponential. So let's say we find the Laplace transform of this complex exponential e to the I omega t. So we integrate from 0 to infinity of e to minus st times e to minus t to the I omega t by dt. So this integral from 0 to infinity of e to the minus s minus I omega t by dt. Now as seen before, whenever we do this integration, it's equivalent to having 1 upon s minus I omega. So we're just taking down what is inside this brackets of the exponent. So then we can say that it's going to have a pole whenever the denominator equals 0 as s minus I omega equals 0, or when s equals I omega. So we were able to say then that the Laplace transform of e to I omega t is 1 upon s minus I omega, and we still have the proviso that the real part of s is greater than 0. So just as the previous video showed, that we can now position this pole at any point s equals I omega, just dependent on our choice of the value of omega. So let's go ahead and we'll see that in Matlab. So this is an output from Matlab, and you can see that we can position the pole anywhere along the I omega axis. So we've actually got the I omega axis here. Okay, so I've just moved it around so it's facing this direction. So that's I omega, and that's the sigma axis. And you can see here in this example that the sigma still remains at the value of 0, but the I omega is now positioned at minus 1 in this particular example. So the example we just seen there was Laplace transform of the minus I omega t, which is equivalent to minus 1 times I omega t. So that's 1 upon s minus, now the I omega is now minus I omega, so it's 1 upon s plus I omega. So we get a pole when s plus I omega equals 0, or s equals minus 1 times I omega. So we've seen there in the previous slide cutting the I omega axis at minus 1. So now we've seen the two possibilities. We can move it in the sigma axis independently, and we can move it in the j omega axis independently. But now what we want to be able to do is move it in the j omega axis and the sigma axis at the same time. So this will allow us to position the pole anywhere within that complex plane. So we're going to use the Laplace transform of a function e to the a plus I omega t. So we've seen there previously, when we find the Laplace transform, we just take the exponent down. So we get 1 upon s minus a plus I omega. So that tells us then that we're going to get a pole when s equals s minus ai omega equals 0, or equivalently s equals a plus I omega. So now we can say that we can position our pole dependent on the value of a. So if a is positive or negative, it will shift along the sigma axis, and we can position the pole dependent on the value of the I omega. So if it is positive or negative, we can shift it up and down the I omega axis. So by choices of this a plus I omega, we can position this pole anywhere within that complex plane. So let's have a wee look at an example of this in Matlab. So here's an example here in Matlab, and you can see that the pole's been positioned here on the sigma axis along here at minus 5, and the j omega axis here at a point 3. So we're able to position this anywhere along this axis. So let's have a wee look at this live in Matlab. So we're going to use the L1 again. So we'll put in this case 1 divided by s plus 5 minus 3i, and you can see I've got the quotation marks again. This is available in the resources section. So whenever we put that in and look at the complex frequency domain, we see that we get our pole here And our pole's going to exist at -5 in the sigma axis, and it's going to be +3 in the I omega axis. So that's us found a way of moving the pole to any position within the complex plane. So thank you for listening to this video. I'll get you on the next one. Goodbye.